Lift and drag coefficients play a strong role in the preliminary design and performance analysis of airplanes. The purpose of this video is to enforce the importance of CL and CD in aeronautical engineering. Consider an airplane in steady level flight. For this case, the weight acts vertically downward. The lift acts vertically upward, perpendicular to the relative wind V infinity. In order to sustain the airplane in level flight, lift must be equal to the weight. The thrust T from the engines and the drag D are both parallel to V infinity. For steady flight, thrust must equal drag. Note that for most conventional flight situations, the magnitude of L and W is much larger than the magnitude of T and D, typically around 15 to 20. For an airplane of a given shape, at a given Mach and Reynolds numbers, CL and CD are simply functions of the angle of attack alpha. Note that CL increases linearly with alpha until an angle of attack is reached when the wing stalls. The lift coefficient reaches a peak value and then drop off as alpha is further increased. The maximum value of the lift coefficient is denoted by CL max. The lowest possible velocity at which the airplane can maintain steady level flight is the stalling velocity, Vstall. It is dictated by the value of CL max. For a given airplane flying at a given altitude, knowing its weight, the density, and the surface, we know from this equation that each value of velocity corresponds to a specific value of CL. In particular, V infinity will be the smallest when CL is a maximum, so the stalling velocity for a given airplane is determined by CL max. Let's keep talking about lift and drag, but now let's focus more on drag. The maximum velocity for a given airplane with a given maximum thrust from the engine is determined by the value of minimum drag coefficient, CD min. From the definition of drag coefficient applied for the case of steady level flight where thrust equals drag, we have this. Solving this equation for V infinity, we get for a given airplane flying at maximum thrust T max at a given altitude, the maximum value of V infinity corresponds to flight at CD minimal. From the above discussion, it is clear that the aerodynamic coefficients are important engineering quantities that dictate the performance and design of airplanes. For example, stalling velocity is determined in part by CL max, and maximum velocity is determined in part by CD min. Okay, cool stuff, but how do we use this information? Over the whole range of flight velocity from Vstall to Vmax, the airplane lift coefficient varies. The values of CL given by the curve are what are needed to maintain level flight over the whole range of velocity at a given altitude. The airplane designer must design the airplane to achieve these values of CL for an airplane of given weight and wing area. Note that the required values of CL decrease as V infinity increases. Examining the lift coefficient variation with angle of attack, note that as the airplane flies faster, the angle of attack must be smaller. So, at high speeds, airplanes are at low angle of attack, and at low speeds, airplanes are at high angle of attack. The specific angle of attack which the airplane must have at a specific V infinity is dictated by the specific value of lift coefficient required at that velocity. Obtaining raw lift on a body is relatively easy. Even your head outside the window's car creates lift at an angle of attack. The name of the game is to obtain the right lift with as low drag as possible. The values of lift coefficient required over the entire flight range for an airplane can sometimes be obtained even for the least effective lifting shape. Just make the angle of attack high enough. But problem is that CD also changes with the velocity. A poor aerodynamic shape, even though it generates a good values of CL, will have high values of CD as denoted by the dashed curve. However, if we design an efficient shape, we will produce the requisite value of CL with much lower drag. A side effect of the high drag shape is a lower value of the maximum velocity for the same maximum thrust. The thing we need to measure to get aerodynamic efficiency of a body shape is its lift to drag ratio, given by this equation. At a given velocity, we want L over D to be as high as possible. The higher is the ratio, the more aerodynamically efficient is the body. For a given airplane at a given altitude, the variation of L over D as a function of velocity is sketched here. Note that as V infinity increases from a low value, L over D first increases, reaches a maximum at some intermediate velocity, and then decreases. Note that as V infinity increases, the angle of attack of the airplane decreases. From a strictly aerodynamic consideration, L over D for a given body shape depends on angle of attack.